Hello and welcome, everyone. My name is Michael Horn. Today we'll be working through some problems in my separations class. And in this video, we will be tackling part A of homework 2. And as you can see on the left side of your screen, we are going to explain and derive the Rashford-Rice equation for VLE equilibrium. We will then show that in a monotonic function of the vapor-Volmar fraction. And then the second thing we have on the agenda, we're going to implement the Rashford-Rice VLE calculation in Python. We're going to explain how the bubble and dew pressures can be used to infer on our initial guess, and then we're actually going to be able to apply that function to the flash calculation according to the specs given. So, without further ado, I will get rid of this, and we will begin working on our iPad. So, let's begin with putting some equations that are going to be the backbones of the work that we're going to do today. As we've seen before in many classes, F, which essentially means the total composition, is going to be equal to our vapor plus our liquid. Now in this situation, we're going to want this. My camera is terrible. In this situation, we're going to want many instances, iterations, so, not n, sorry. I can be equal to 1, 2, 3, all the way to whatever you prefer. And so now you're going to rewrite this equation into ZIF equals YIV plus XIL. Okay, I think I fixed the camera, hopefully. So now we want to actually break this term down even more. And so we're going to divide everything here by F. And so we're left with ZI equals YIV over F plus XI L over F. Now, this may look even a little more complicated than the last equation, but it's not, because we're able to actually make a variable of our vapor fraction, which is going to be this phi equals that. And then this liquid is going to be actually whatever is left over from the vapor. So we're able to rewrite this as ZI equals YI times our phi variable plus xi times 1 minus our phi variable. And again, that's because whatever is left over from the vapor is going to be in that liquid. Okay, so sorry for the sirens. Hold on, I want to pause. So now our purpose is going to be isolating yi and xi, which yi is the vapor, xi is the liquid. So the first thing we're going to do is create this ki term, which is actually going to be equal to yi over xi. And so let's first, actually then you're able to realize that yi equals ki xi, and this is going to help us actually isolate this xi variable first. So what we're going to do is take this and plug this in right there. So we have zi equals ki xi phi plus xi times 1 minus phi. Now we're going to distribute this all out. Zi equals ki xi plus minus xi phi. Now we can take out that xi. And the last step would be to get xi by itself. Now, the final step is going to be, I'll draw this up here, the summation of xi on one side, take the summation of the other side, which is zi over ki phi plus 1 minus phi, and that is actually going to come out to 1. So the summation of xi is going to be equal to 1. We'll highlight this, And now we're able to move on doing the same thing for our yi term. And so in this situation, we know that xi is equal to ki over yi. And now we're going to do the same thing, but swapping in this term wherever we see xi. So we start out with zi equals yi phi plus ki yi times 1 minus phi. Let's distribute everything out. A lot of algebra today. Now, the next step will be isolating yi, in which you're actually going to want to multiply. I'm sorry, I realized I made a mistake here. This is supposed to be flipped right there. This is meant to be yi over ki. So these are all flipped. There we go. yi over ki, yi over ki. Now, the next thing we're going to do is multiply all these terms by ki. So you get ki zi equals plus yi not. Now again, we want to isolate that yi term, so we will take that out. Get ki zi equals yi times ki phi plus 1 minus. And you realize, oh wow, that looks very similar to this term that we had earlier. So now you're going to continue this process to get yi alone, and you result in yi equals ki zi divided by that term that we recognized, in which again, we're going to write this up here, take the summation of both sides, and you left with the summation of yi equals 1. Now we have a little bit of work left to do before we arrive at our final equation. And to do this, we're going to look at, okay, well, this is equal to 1, and this is equal to 1. So kind of just using intuitive thinking, you could go, okay, well, the summation of x1 minus the summation of y1 is then equal to 0. Okay, yeah, that makes sense. Actually, let's flip these around, just because I know it's going to make it easier in the future. Now, okay, so yeah, that makes sense. But let's take this a step further. Let's substitute what we actually know in. Let's say, okay, well, the summation that we know here as ki zi divided by 1 plus ki phi minus phi minus the summation of our x term, which is zi over the same thing, 1 plus k phi minus phi equals 0. Right, now we can even break this down even more, and you are left with the summation of common term zi times ki minus 1 over our common denominator of 1 plus k phi minus phi. Is that ki? I believe that's ki, yeah, I'm sorry. I've been forgetting the I in here, so Pardon my mistake. Let's rewrite that. And this is going to be equal to 0. Now we have arrived at our big final equation. Ratchford Rice helped us get here, and we're able, to move into Google Colab. So as you can see, we are in Colab now, and the first thing that we want to do is to define our flash pressure temperature. So define flash PT, and then we want our Z value obviously, and then our P and our T. And then next, let's add our column there. Dew pressure, we want to set equal to dew P, and those are functions of Z and T. And we also want our dew pressure. Sorry. So this is dew pressure. They also need boiling pressure. I don't know why I said boiling. Bubble, and that is Z and T also. Now we need to create an if statement to show whether if it's all liquid or all vapor. And so we're going to say if our pressure is greater than our bubble pressure, we want to return an all liquid statement. This is saying that obviously if that pressure has gone above our desired bubble pressure, then it's obviously all going to be all liquid. And now we need to do the same thing if it's all gas. So we're going to get rid of this. We're going to say if our pressure is less than our dew pressure, we need to return all gas. And then we also need to make our phi gas. So we're going to understand why it's being so weird. Here we go. Phi underscore gas equals, and that's equation for this is going to be our bubble pressure minus our pressure. Here we go. Gemini's going to finish it for us actually. Thank you. And then we also need to set what our K value is equal to. And our K value is going to be equal to P dot P vaporization of value temperature divided by our pressure. And then the final step in this is going to be defining fruit, which we have done before here, which is phi. And then we are going to want to return J and P sum, and then we have a long equation here, which is going to be our Z value times K minus 1. This is because when you know one part of K, the other one's obviously going to be minus 1 because that will finish out your vapor fraction. And then we want 1 plus phi times our K minus 1. So now we just have a couple more fruit functions to put in here. We need fruit prime. And again, we're going to use Jax here, just like we have previously. We need Jax dot grad fruit. And then we also need fruit equals Jax dot git fruit. The last step will be actually plugging in what our phi is, what our x is, and our y. And that is going to be phi equals sp.optimize. And that is close to what we want. So we are actually going to put that in there, but then this method is not going to be secant, it's going to be Newton. And then we still need to add a section that says f prime equals fruit underscore prime. And then, as I mentioned before, I need this to go away. There we go. And then we also need to define our x and y value. X is going to be z divided by 1 plus phi times k minus 1. And then our y is going to be equal to k times x. Again, we got these equations from the Rashford-Rice equation that we derived earlier in this video. And then we are going to want to return phi y and phi x y. Alright, so let's see how this runs. So we are good, we have all the green check marks, and we are able to actually go now into our array in our plotting portion of this problem. So let's complete the last portion of this, in which we actually do our flash calculation. Flash PT, we want an array. This is not going to be a plot, this is actually going to be just a numerical array. Just 1E5, 70, and let's see what we get. It has no attribute fit. Let's explain this error. I'm going to pause and try to figure this out. This was actually a very simple fix. Gemini was telling me to do a bunch of weird stuff, but I realized I accidentally had fit here instead of JIT, so I put JIT in. Now we're able to look at our vapor fraction. Actually, here's 0.297, call it 30%. And then here in our liquid fraction, it is 33% benzene and 33.5 and then 66.5 toluene. And then here in our vapor, we have 55% benzene and 45% toluene. So this has been the conclusion of part A of homework 2. Thank you for watching.